Hello, everyone. Welcome to PyData Global 2021. I'm Conrad, one of the co-chairs of the conference, and we're super happy to welcome Oliver here to talk to us about machine learning and health predicting pregnancy complications. Thank you.
Thank you very much. So I'm going to share my screen. Welcome, people. I'm very happy to be able to present here. Talking to people from all over the world is really exciting, and I'm quite a bit nervous, but yeah. So I'm going to talk about PreFree, which is a very specific use case that we are working on right now, and the topic is we want to predict pregnancy complications with health with machine learning. And yeah, let me start by a short introduction. So my name is Oliver Rieger. I'm born and based in Berlin, Germany, and my origin is mathematics and astrophysics. And I've been working as a data scientist in the German industry since 2015, mainly at the wonderful company with the wonderful name, Unbelievable Machine Company. I've been working in the data science department as doing projects throughout the whole German industry, often car manufacturers, of course. Since 2019, when my son was born, I'm working as a freelancer, and since April 2020, I'm happy to work as the tech lead for the project PreFree. So what will the content of this talk be? First, I will give you a one-liner about PreFree, and then I will, of course, do a deeper dive into the medical case behind the problem, the disease called preeclampsia. And then I will get technical and talk about the application, about the structure of the application and the tools we're using. And then I will, of course, talk more about machine learning, providing hopefully all the details that are of interest. And in the end, I will give a short slide about data protection, because we are dealing with very sensitive data here, of course. So let's quickly start with the one-liner. What is PreFree? What is machine learning? PreFree is a machine learning powered clinical decision support and home monitoring tool that helps clinicians to manage pregnancies at risk for preeclampsia and predicts related complications. Okay, long sentence, a lot of special words, especially preeclampsia. Let's talk about preeclampsia first. What is that? What kind of disease? So preeclampsia is a multi-system disorder in pregnancy. That means that it can affect the whole body. And it has actually a quite high incidence worldwide. 2 to 5 pregnancies per year worldwide are affected by it, and it's the leading cause for maternal morbidity and mortality. And to give some shocking numbers, we are talking about 10 million cases per year, 500,000 babies lost per year, and 76,000 maternal deaths. So, okay, what is preeclampsia? Preeclampsia, the main characteristic is that the symptoms are very unspecific. That means that the women show symptoms that can be caused by many other reasons. So they present with headaches, with weight gains, with elevated blood pressure, with protein in the urine. And on the other hand, on the other side, preeclampsia can lead to very severe complications. The women can have brain hemorrhage, the kidneys can fail, there can be an early birth of the baby, the livers can take heavy damage, and there can also be eclamptic seizures for the women. All things that put a high risk on the mother's health and the baby's health. And that there is a gold standard for diagnosing preeclampsia, but it's just based on blood pressure and protein levels in the urine, and it provides only a positive predictive value of 20%. That means to detect to predict these complications, we call adverse outcomes. That means that 4 or 5 women that have the diagnosed preeclampsia by this gold standard don't actually develop these adverse outcomes. And this is where this actually leads to the following situation. Whenever a woman presents at the hospital showing signs and symptoms of preeclampsia, the doctor has to gather all the data, all the information about their symptoms, or has to take blood, he has to measure her vital signs, get as much information as possible, and then from this information, and also very important from his own experience with cases, he has to decide whether to keep the woman in the hospital, or because he is afraid, or it could be that there is an adverse outcome on the horizon, a complication, or to send her home. And because this is a very difficult decision, this leads to many women staying at the hospital for, now I wouldn't say no reason, but it turns out after the delivery that 80% of them would not have had to be in the hospital. And this is a stressful situation. User research confirms that pregnant women, it's not easily said, it's not nice for pregnant women to stay in the hospital also for a long time. And they would mostly have preferred to stay at home. And also the uncertainty, knowing that there is the risk for something, but not to know if it's going to happen, is a big stress factor for the women. And of course, also the clinician would love to be able to better predict if there is an adverse outcome on the horizon or not. So, and this is where PreFree comes into place. We are training a machine learning model that helps the clinician to stratify the risk for adverse outcomes. And we are also giving the women, when they go home, an app where they can at home measure their blood pressure and other symptoms and other vital signs and symptoms, which are then in real time transferred to the system PreFree and presented to the clinician. So the situation before was that the clinician, if he sends the woman home, he tells them to come back in 2 weeks and in the meantime, every day measure their blood pressure and on a sheet of paper and then bring it back in the next visit. So there we are already improving the situation. Okay, let's get technical. So the PreFree application is built up in the following way. The front ends are the physician front end and mobile app for the women. The front end and the biggest part of the backend application are built with Django. Our database is a PostgreSQL database. And for the mobile apps, we have been using React Native. And we are very happy that we have an iOS, Android, and a web app version. So we are confident that most of the women that have a smartphone can use PreFree. Our models serving app is, we are only using scikit-learn models, and we are serving them with fast API and containerizing the application to serve these models with Docker. The whole system is running in a clinical data center. I think I forgot to say that this is a Charite project. That's the biggest clinic in Berlin, and the whole system is running in the clinical data center, and we have a test and production environment. The whole system was built by an external service provider, so this is built in a robust, secure, and professional way, which I'm very happy about. So let's give a short glimpse into the physician front end. So here's the place where all the data from the women is gathered. so the medical, the mobile app measurements, as well as the clinical measurements, and they are displayed to the doctor, so he can, in an interactive way. We are not yet presenting any model predictions, because we are planning to do a multi-center study at the next step, where we don't want to see the predictions, because we want to evaluate our models. We want to see how well they generalize. And the whole front end here, of course, I said it's built in Django, and this visualization here is built in Plotly.js. The mobile application, just a short glimpse here. There the women can put in their blood pressure, they can put in the protein levels in the urine, and they also can put in symptoms. It's, as I said, built in React Native. And yeah, so let's get to the machine learning part. First important thing, data. So what we're dealing with is what the medical world calls real world data, which means nothing else that it's not data that was collected during a prospective study. A prospective study is a very, very highly regularized way to collect data. Our data is collected from the clinical systems, and it's the data that was produced during the clinical all-day work from mid-2010 until the mid of 2019. And the bars, the height of the bars indicates the number of patients per month that are included in our data set. Let me just mention the way this data was extracted was that actually people sat in front of the clinical software systems and transcribed manually all the data points into an Excel sheet. That's 2021. Okay, what do we have in a specific data point? We have, of course, from the women, we have their medical history data, their anamnesis data, age, height, body mass index. Gravidity is the number of pregnancies the woman had, parity, the number of births she had, and many more. And also we have the measurements from the visit, like blood pressure at the visit, or the protein measurements, or important blood markers. And we, of course, have the outcome data, date of delivery, details about the baby. And of course, our important labels, was there an adverse outcome, which adverse outcome was there? Yeah, and of course, multiple visits are possible. All these informations, all these features sum up to more than 60 features in total. So one of our first tasks was to select a subset of relevant features. So as a preparation for this project, the medical staff just collected everything that they had about the patient. And our task then was to filter out the relevant information for predicting adverse outcomes. And that's the next slide, to just state, okay, what was our goal for the modeling? The goal was, of course, to quantify the risk for an adverse outcome in the next X days in a certain time frame. And our labels we had for that was labels provided by the medical staff if there was an adverse outcome after the delivery, present or not, and which one, and the date of delivery, because many of all of the adverse outcomes are closely related to the date of delivery. So our modeling workflow was like this. We did a 19-10% train test split, putting test aside, and then focusing on the 90% training set with a cross-validation. Because the data set is comparatively small to machine learning standards, we iteratively did experiments tracked with MLflow to do feature selection, feature engineering, model selection. We only used scikit-learn also for regulatory reasons, because scikit-learn is the most established machine learning package and probably the best. Okay, I don't want to. It's just, for us, it's very important to use packages that we can trust on. So, and not to use too many packages, because developing a medical product means a lot of documentation. And yeah, just a short excursus. And finally, we, of course, if necessary, we did a hyperparameter tuning and we evaluated on the 10% test set. So let's get into details about the steps in between in our experiments. Feature selection, as I said, we had more than 60 features to choose of. And the easiest first step was to visually inspect distributions. We looked at, we grouped by our interest, by the target we were interested in, and looked at the distributions of the feature. We also calculated feature importances, or we looked at feature importances from tree-based methods. And we used Shapley values. Here, this is a plot from the package SHAP, collected Shapley values of every feature for all samples. This is an example plot from the Shapley package. I'm sorry, because I can't share actually a plot from us because it's currently in a paper under review. SHAP is a package that I like a lot. I highly recommend. I think, yeah, it's great. So what we also did was recursive feature elimination using sklearn methods. And we, of course, also did the classical correlation analysis, calculating Pearson correlation coefficients. And we also had a lot of discussions with the clinical personnel and with collaborating statisticians about the final selection of features that we are using. Then our missing value handling was quite simple. We dropped all rows with less than 50% values present, and then we grouped by gestation week and imputed the median. We imputed the median because some blood markers have massive scales, and the gestation week is basically a measurement, or yeah, a pregnancy has 40 weeks. And each week is a gestation week, and you numerize them from 1 to 40. Another very interesting, from my perspective, approach in terms of feature engineering was the integration of deviations from norm values. So for some features there are so-called reference ranges out there in the medical research. So meaning distributions over the gestation week and over this specific feature that tell you what the normal development of this value throughout the pregnancy is. And we then used these reference ranges and calculated deviations of our measurements from these normal values. So we presented our models kind of values. We presented them features. How are we deviating from a normal pregnancy, or to be more precise, from a pregnancy without preeclampsia? Another picture that might make this clearer is, so this is the x-axis is the weeks of gestation, the y-axis is the scale of this feature that I'm looking at. It's an important blood marker, and the gray dots are the measurements from the study which derived the norm ranges, and the lines are modeling the distributions through overall gestation weeks. So we see this marker is heavily changing throughout the pregnancy. And so if the blue dot was one of our measurements from our data of these two plots, gestation week 30 and gestation week 35, we would then calculate as a feature the deviation from the median, for example. We, based on these norm values, we calculated a lot of different features. Also very common in medicine are multiple of medians and similar things. These deviations from median actually proved quite useful and are in our final model. Model selection. So throughout the experimentation phase, we trained logistic regression, random forest, and gradient boosting classifier. We looked into, in our first exploration, before this phase, we also looked into other models, but like support vector machine and very simple neural networks to model interactions. But it was clear, very fast was clear that we are constricted by the size of our data. Very interesting in regards to model selection, the logistic regression was almost always on par with gradient boosting and random forest in terms of performance. And we were very happy about this because there is still a high skepticism in the medical world about complex models that are not easily explainable. And on the other hand, they all know, any medical staff that does research knows a logistic regression, and they would trust more logistic regression than a handcrafted neural network or even a gradient boosting classifier. So we are keeping that aside if these black box concerns arise. The random forest was interestingly regularly overfitting on our data. For our hyperparameter tuning, we used HyperOpt, a very nice package that I would highly recommend. Yes, and I think I have to speed up a bit. Our resulting model performances were up to 90% ROC AOC and on our test set. And to estimate our generalization performance or our variance of our possible generalization performance, we did the following. After our modeling phase was finished, we let the random seed loose, so to say. So we actually evaluated our models with a multitude of 90-10% test split, train test splits. And then we measured the scores on the test sets and printed them here. And so this box plot on the very left side shows that one of our models had a high variance depending on how we did the train test split. This was, we were not happy to see this, of course, but now I can say that we got another data set for evaluation from a very different from another continent and a very different population, and all the models that were trained on all the different 90% training sets, all evaluated very, very strong and very good on this external data set. So we think that through the manual transcription of the clinical systems into the Excel sheet, there was a lot of noise introduced. Maybe there was also before a lot of noise in our labels. This is so as the clinicians or the medical world says, real world data. But yeah, seeing that we are well performing on an external data set that was actually gathered from a prospective study was very, very nice and relieving. So what are our next steps in terms of modeling? We are planning to do a probability calibration, and for that we are extracting additional data from our center at the Charite from 2020. And we are also, I said before, we are planning to do a multi-center study in Germany where we evaluate our models on different centers throughout the country. And we're talking to many different centers throughout the world if they would give us their data to evaluate our models. Yes, how did we deploy our models? Straightforward. We only have scikit-learn models. We pickled them. We served them with fast API, and we containerized them with Docker. The data protection side, a very important topic. It's medical data, so we have to be very sensitive and careful about that. So during the modeling, we used only pseudonymized data, no names, etc. were in there. We transferred the data between the team only encrypted, and the data is also only saved on encrypted hard drives. And of course, we are all very sensitive about this type of data and very, very careful and of how we use our day, how we work with our laptops in the all day. Yeah, making sure that it's always locked when we are not sitting in front of the laptop. And so we have to be very careful there. And the system itself is hosted on site at the Charite, at the clinical data center. So they are taking care for data security in the same way they are also taking care for all the other medical data they are hosting. And as I said, our complete system was delivered by a professional service supplier with a high focus on security. There is nothing, so to say, hacked together. Yeah, and we are also planning a security review through an external auditing company for early 2020. Yeah, so I'm actually at the end of my talk. I'm happy that I made it within the time, and would be great if there are other teams interested in what we do, or maybe working on the same problem, or also decision support system, or are just interested in our case and like to talk to me. I will be available on Slack and happy to answer any question. And of course, there are also some open challenges and questions we have to deal with. We still want to improve our missing value imputation. We want to know and learn how we can detect and handle out of domain data. And we also want to reduce the data input time for clinicians, and are very worried about data silos at the hospital that don't allow connections to them. That's an issue. So thank you very much for your attention, and yeah, looking forward to talk to you all. Thank you.